Hi everyone, this is Ashwin here. In this video, we're going to see about how to create an image segmentation model using UNet. So this is the common model which is being used for image segmentation, and there are many variations of this model that you can definitely use, or you can also create your own image segmentation model. But the tutorial completes the end-to-end flow. You can change any part that you would like, and for this I'm going to use Oxford IIIT PET dataset, which is a common dataset for image segmentation if you are a beginner. Now you have to connect to the GPU, but for now I'm just connecting to CPU to save some compute units. So let's connect to it, and we will start importing modules. Import modules. So once all the code is ready, before doing the training, we will try to enable the GPU and start the training. Now we are going to use TensorFlow for this tutorial. So I'll import TensorFlow from TensorFlow.keras, import layers and models. Okay. Now from TensorFlow dot datasets, I think underscore datasets as TFDS, which represents TensorFlow datasets. So this will be from import, and finally we will import NumPy array, and for plotting purpose we will use matplotlib. pyplot, I think I'm doing so many mistakes at the start itself. Let's see. Okay, now finally matplotlib inline. Let's run this. Okay, it ran without any issues. Now we have to load the dataset. Load the dataset. Now dataset comma info equals tfds.load. So TensorFlow dataset has already got the Oxford IIIT PET dataset. So Oxford IIIT PET. So there are multiple versions of the dataset. You can also specify the version. If you just leave it as it is, it will fetch you the latest version. And with info equals true. Okay, let me run this. I got a few crashes when I tried to download the dataset. I'm not sure why that is the case, but after restarting the session, once the dataset is downloaded, we can normally use the dataset as it is. As you can see, it's downloading the images that is present. After that, I think it will do the extraction. So let's wait for some time. So in the meantime, while the dataset is getting downloaded, we will start the next steps. See, the session got reconnected again. So this is the problem which I faced earlier. If you are using Colab, I think you would face this issue. If you have the dataset, you can directly load the dataset as it is. Let this reconnect. In the meantime, we will add the preprocessing functions, or we will define the preprocessing functions, preprocessing steps. So for the image, we have to define normalize function, input image, and input mask. So input image is the original image, mask is the masked image of the input. So we have to normalize both. So input image equals tf dot cast of input image and we are just converting to floating point and divided by 255. So this will normalize the pixel values, and this will convert to in the range of 0 to 1. And input mask -1 and return input image comma input mask. So before doing that, we will run this cells again. Okay, now it loaded the data set without issues. Let's see the information first. So this is the complete data set. What are the columns that are available? File name, label. It has like 37 classes of different pets, and here you can see the image, and this is the segmentation mask or the mask image, and this is the version of the data set. I think that's pretty much it. We have both train and test for this with this number of examples, and let's see the data set. So you can see file name, image, label, segmentation mask, and species. So we will use only selected columns, especially the image and segmentation mask for our tutorial. I forgot to explain about why we are negating the mask by -1. So the mask will contain 3 integers or 3 dimensions, which represents like different colors for the pets, which I will show it in the visualization. So it will start the index from 1. So in order to convert it to 0, 0, 1, 2, I'm using -1. So it will convert it to 0 based indexing. So I will add a comment. 0 based indexing. So it will be easier for us to process, because pretty much for most of the data set we start the labels from 0, and we will load the image train. Load train image. Will pass the sample or image sample, whichever you like, and input image equals tf dot image dot resize sample of the image, and the resize value, I'm going to convert this to 128 cross 128 because that is sufficient. So resize the image, and we have to do the same for the input mask. Input mask equals, we'll do the same process again, but the sample will be segmentation mask. And for training data, we can do some data augmentation. So for that, if tf dot random dot uniform, I'm just randomly getting the value in the range of 0 to 1. So if it is greater than 0.5, like 50% of the data will be augmented. I'll do input image equals tf dot image dot flip left or right, input image, and input mask. We will do the same thing. Okay. Now input image and input mask will be normalized. I will add that comment here. Normalize the images. normalize input image. So this will just do a horizontal flip. Up and down means it will do a vertical flip. So horizontal flip means it won't change the data as it's a pet. Pets won't hang from the wall. If you do flip up and down, that will be the case. And pass the image and input mask, then return input image and input mask. So this is for the train images. Now we will do the same for test images, but we don't have to do augmentation for the test images. Just change a few things. So we will do the resizing as it is, but we don't need the augmentation part for the test or validation image. Rest of the things will remain the same. So this is the preprocessing functions. Now from the dataset we will split train and test dataset. Train dataset equals dataset of train dot map of load train images and num parallel calls, num parallel calls. So this will do some parallel processing with the available cores. To do that, tf dot data dot experimental dot auto-tune. Now we will do the same for test data. So dataset of test dot map load test images, and we can also do the same. Let me run this. Okay, now this is done. We can define the batch size and buffer size for the datasets. So batch size equals 64 and buffer size will be 1000. So this is some optimizing of the data loaders. For most of the process we don't use it, but TensorFlow currently allows us to specify number of cores that you want to use for speeding up the IO processing. Now we will use the train dataset dot cache dot shuffle buffer size. So this will use the 1000 samples to shuffle in between instead of the whole dataset, and batch it. We will use the batch size and repeat the process, and then dataset train dataset dot prefetch of buffer size equals, have to use the auto tune here. Auto tune means it will automatically check the number of cores or availability and use it accordingly. So this will save some memory overflow or crashes. So I would suggest to use this. And then test dataset, we can just have the batch size for test dataset, batch and batch size. Okay, let's run this. Now we will do some EDA. So the dataset is ready for processing. Explanatory data analysis. So I will display the image and the segmentation mask and see how it look like. Def display sample and image list plot dot figure fig size equals 15 cross 15. Then we can have the title equals, so I'm just using the same function for when we are doing the test phase. So I will have input image, the true mask and the predicted mask. So for now we will only pass input image and true mask, but for the test phase we will pass all three of them. So for in range of len of image list, based on the size we will display that much alone. So plot dot subplot of 1 comma len of image list and then I plus 1, which will be the index, plot dot title of I, and then plot dot im show. I can use np dot array of image list of I. If this does not work, means we can also use inbuilt function of okay, we have to convert this to image, so we cannot use this. So there is a function in Keras returns array to image. So this will convert the array to a image format, and then plot dot axis of finally we will display it, plot dot show. Okay, let's take some 2 or 3 samples and display it. For images comma masks in train dataset dot take, I can have like 3 samples. Now sample image and sample mask equals images of 0. It will have like additional dimension because of the batches. That's why we are using the index to extract only the images. Now I will use display sample, pass the sample image and sample mask, sample image and sample mask. Let's run this. Okay, it should be a list. Okay, now you can see the input image and the mask. You can see some blurriness because it converted to 128 cross 128. That's why we can see some blurriness, and you can see the animals are segmented with these colors, and you can clearly see how the segmentation looks like. So the violet color represents the animal, and the green represents the background, and the borderline represents the outline of the animal. I think we could reduce the size a little. 10 cross 10 would be sufficient. Okay, this is somewhat clear. Now these are the sample images. Okay, now let's define the model. Define UNet model. Again, there are many different models that are available for image segmentation, but UNet performs much better compared to the others. That's why I'm using it. So in order to avoid the ease of building the layers, I will define multiple functions or utility functions to build the layers. So def double convolutional block. And if you don't want to see me like building the model from scratch, you can definitely skip it and proceed to the training part. But this would help you to understand how this works. We will have two convolutional layers here and pass the result. So layers dot con 2D of n filters 3, padding will be same, activation will be relu, and kernel initializer equals he normal, and we will pass the input which is x, and we do the same again and return x. So this is the double convolutional block. We will use this to upsample and downsample the layers. First, when you pass the input image, we will try to downsample it and extract the feature. So def downsample block. Here also we will pass x and n filters. A forward block, we will use double con block, pass the x and filters. Then we can do max pooling, and this forward block will be connected to the upsampling block. So if you are doing max pooling, layers dot max pool 2D of 2 and pass the forward layer, and if you want dropout, you can specify it here, dropout of 30%, pass the pooling layer, and we will return both f and p. Then def upsample block x con features and n filters. This con features will be coming from this downsampled block. So n filters. So here we have to do a con 2D transpose, layers dot con 2D transpose of n filters, then the stride 2, and padding will be same, pass the input. Then we will concatenate both the x and con features. So x equals layers dot concatenate. Many new models have this concatenation of previous layers, which improve the model performance. After concatenation, have the dropout, layers dot dropout of, again we will have the same percentage, pass the input. Finally we will use the double con block again, x equals double con block x comma n filters. So this will be the upsampling block, return x. Now I will use these functions to build layer by layer. Now def build UNet model. We have to define the output channels here. We have 3 channels, which is a RGB image as a segmentation mask. Sometimes you can also deal with grayscale image. So in that case, the output channels will be 1. First, inputs equals layers dot input. So this will capture the image. Have to define the shape. which is 128 cross 128 and a 3-channel image. Then the encoder, which will compress the image features, and this will downsample f1 p1 equals downsample block of inputs comma 64, and we repeat the same thing again and again. So f2 equals p2 downsample block of, you will pass the p1 here, which is the pooling layer, and increase the filters to have it reduce the size. So f3 p3, again a downsample block of p2 and 256, f4 p4 downsample block of p3 and 512. After this we will have a intermediate block. So after this intermediate block, we will upsample the features to have our final masked image. So here we will use the double convolutional layer with p4 and 1024, and this will be the decoder or upsample. Now u6 equals upsample block of intermediate block comma reduce the number of filters 512. Okay, so here with this block we will connect the previous layer, which is f4, which is the forward layer. So like this we will do the same for the rest of the upsampling layers. So u7 upsample block, now u6 will be passed, and f3 higher, again we will decrement 512, so this will be 256. We're just incrementing in the power of 2 and decrementing in the power of 2 for the filters. Now u8 equals upsample block of u7 and this is f2, right? f2 and 128, and u9 equals upsample block of u8 and f1 64. So we got the similar dimensions at this point. And finally the output layer, thus we can say it as input layer. Outputs equals layers dot con 2d of output channels. Based on the number of channels, it will use the output. Same activation relu and pass the u9 layer. Okay. Now finally we will define the UNet model. So UNet model equals tf dot keras dot model of inputs outputs, name will be UNet, return UNet model. Okay, now let's define the output channels, which is 3, and model equals UNet model of output channels. This would be build UNet model. Then we will compile the model with the loss and metrics along with the optimizer. So optimizer will be Adam, and loss will be sparse categorical entropy. And if you're using grayscale, I think you would be using binary cross entropy. Metrics will be accuracy, as it's as we are using categorical entropy here. And if you have some doubts like how the mask layers would look like, you can reuse this same snippet. So just take only one, get the sample mask and print it. So you can see all of them were defined as 1. Only the highlighted layers will have a different numbers. I think some of them are hidden. So here when I used a sample mask of 60, just those index, you can see it has 2, 0 and 1s as well. So that's how the labels will look like. That's why we have those 3 channels. So other than this format, you can also define it as like a pixel formats if you want, like in the range of 0 to 255, and just highlight only the mask values as 1 if you normalized. So that is also you could do. So I will have this as a comment if you want to explore that. Now let's compile this. Okay, this is kernel initializer. Let's run this again. So this would be inputs. I think I made a mistake here. Let me run this. Okay, I think here I used con 1D transpose. This should be 2D. So again, this mistakes is very common when you are building the model. You have to make sure everything is built correctly and check it in the graph. Again, activation. Okay. Yes, I think this video I have made many mistakes, at least at the start and in the model building. Now the model is compiled successfully without issues after multiple changes. So the changes which I done is activations. It's a common mistake. And here in the con 1D transpose, I think intention was 2D. I missed it. And here also initializer, you have to add the R. So that's all the changes that you have to do. So let's change the runtime to GPU, as we have done most of the coding part. Okay, now I have changed the instance to a GPU and rerun everything. Now if you want to plot the model, you could do that. Plot the model, tf dot keras dot utils plot model. of model show shapes equals true, expand nested equals false to avoid a bigger size of the graph, and DPI equals 64, just the pixel format. Now you can see the full model. Now this is the input, and these are the each downsampling we are doing. You can see how the images are changing each time, or how the layers and the inputs and outputs are changing. Once we meet the intermediate layer, we are concatenating with the output of the previous layer, and we are again upsampling, as you can see here. Until here we have done it, and finally we are making the output. Okay, now let's train the model. Train the model, have the epochs equals 20, steps per epoch equals info dot splits of train dot num examples to see how many examples are present in the dataset. If you have some kind of array, means you can just use length of the total dataset, and we'll divide it by batch size, and then we will do the same for validation steps. Validation steps equals info dot split of test dot num examples batch size, and finally we will train the model. History equals model dot fit of train dataset epochs equals epochs, then steps per epochs equals steps per epochs, and validation steps finally we have the validation dataset equals the test dataset. Okay, let's run this. Dataset object as no attribute split. Okay, this is splits. Let's run this again. I think I am pretty much missing all the plural form. Let me just double check. Okay, this is validation data, and let's run this. Okay, I think in the compilation this is sparse categorical cross entropy. Okay, now the epochs are getting started. Let me check the usage. Here you can see the GPU usage shot up. Depends on the model you are using. You can decrease the batch size if you are running it in your local machine. As you can see, it pretty much maxed out the GPU VRAM. We have to wait like until at least the first epochs progress. Until that we have to wait whether some issues are popping up or not. But yeah, this video I have faced many issues compared to all of my previous videos. Okay, now that you can see, it started the process. So we have to wait until the 20 epochs are done. So after leaving it for some time, I can see it just stopped at 05461. It was pretty strange. So I just checked the model and I didn't update the activation layer. This should be soft max, as it's a categorical loss we have initialized. So we have to do the training again. I have like stopped the training in between. So until the training is complete, we will complete plotting of the graphs or visualize the results. Visualize the results. Plot, train, and val accuracy. So plot dot figure fix size equals 12 4, and we will use a subplot here. So plot dot subplot 1 to 1. I'm going to display accuracy and the loss, that's why. So plot dot plot history dot history of accuracy, and then we will repeat the same. Okay, this is history dot history of val accuracy. Then we have to give a title. I will say model accuracy. Then plot dot x label, which is epochs, and plot dot y label will be accuracy. Then plot dot legend. Okay, if you want like train or validation, you can also do that. So train val and have a location. So loc equals upper left. Okay, let me also check the results. Okay, now the val accuracy didn't stop at 0.54. It improved. Let me just check this validation accuracy. So it improving, so we are good to go. Now we will plot train and val loss. Here we will just use the same snippet, just change few things. So this will be the second graph, and this will be loss, and this will be again loss, model loss, model loss. This would be loss, and everything is good. Now plot dot tight layout and plot dot show. Okay, so this will give us two graphs which will show the accuracy and validation. And finally we need to get a prediction from the model and display it how it looks like. So test predictions. So def create mask of prediction mask. So prediction mask equals tf dot argmax of prediction mask, and access equals -1. So based on the probability values or logics, we will get the index, which is 0 to 2, we have like three classes, right? 0, 1, 2, which represents the background, the outward layer, and the pet itself, which is the segmentation part. So we will take the argmax and pred mask and have a new axis to have it in 3 dimension, and tf dot new axis. Now return pred mask of 0. If this is confusing, means we can also print in between to check the layers. And after this, we will do the prediction. Def show prediction of dataset. By default it will be none, and number of samples will be 1, like a single sample. And if dataset is present, then for image comma mask in dataset dot take of the number, how many samples you can give it in the function. Then prediction mask equals model dot predict. So we are predicting 1 by 1. So I will pass the image. Then we can plot it using the display sample function at the top. So we will just run this, or what we can do is we will return pred mask, just to understand what's happening inside. So after returning, I will have show predictions. Okay, this should display the whole thing. So what I will do is I will make this function for displaying. So display sample of a list, and inside it image of 0, mask of 0, and create mask of the prediction mask. Okay, now this is done. We have to like run this again. At least for testing purpose, we will just have this alone, and we will see how the pred mask will look like. And then we will pass the create mask, or whatever happening inside, we will implement it step by step. So pred mask equals, just copy this and paste it. Again we will display the pred mask, and after this we will get the shape and see how this look like. So what I am going to do is I will just wait for some time for the training to finish, because without this we cannot plot everything and complete our testing process. So I will wait for all the 20 epochs to be done. As you can see, it's taking around more than a minute. So I'll wait for this one. Now that the training is completed, it's still showing it's running, but the training is completed and we got good validation accuracy and the training loss. Let's run this. I have, while copying, I just copied this as well. Just remove that. We just need to have a single figure, or else you will get 2 figures. Run this. So this is the model accuracy and this is the model loss, and you can see it's steadily increasing, and I think based on the curve you can still train it for some more, around like 10 epochs maybe, and see how the accuracy improves. And let's do the test prediction. So let's run this one and run this. Okay, this will be test data set. Okay, now you can see it has three dimensions, so all of them having some probability value. Based on the index, doing this argmax, it will have only the maximum integer. Let me just run this one. Okay, now you can see based on the argmax is just reduce the number of dimensions, and here you can see most of them having 1 and this one having 2, and if you check the intermediate layers, it will have zeros, which is the segmented image. And we have to check the shape as well. Let me check the shape of this dot shape. So now you can see it has 64 comma 128 cross 128. Let's copy this one and see what it does. And spread mask dot shape. Let's run this. So after this, you will just take the 0th index from this. So that will be this spread mask of 0. So the dimension will be 128 cross 128 with a single dimension. So spread mask of 0 dot shape. So this would be the final shape you will be getting. So let me just comment these parts. You can have this as a reference, and I will combine everything to a single cell. I will print this. Should be np of array, or else it will show some error. And then finally we'll have this and print it again. Okay. Now that you understand how the prediction mask is changing to our desired results, you can comment this one. And let's check the final predictions. Now we can use this show prediction to do that. Show predictions of test dataset, and I will take 10 images from it. Let's run this. Okay, this is, I will add yes here. So it's doing the prediction, the true mask and the prediction mask. So here for these images, the prediction is pretty accurate, and for this also, this is good. Majority of them are covered, but this part is getting missed. And here also, it's also covering this chair in this prediction, and the major parts are getting covered. So for some minor parts, it's getting confused, and these are all pretty good. This is good. This is also good. I think caller we can ignore that. I think for consideration, I think our model is performing better on the segmentation task. And as I said before, you could train for additional 10 epochs and see how the results are looking like, and it will definitely improve the results. Or you can also change the model for a different model which performs better than this basic UNet model. That is also you can try, and let me know in the comments how much the results has been improved. And that's pretty much it, guys. So this is how we can do segmentation of any image with any of the data set. If you have any queries about this video, please leave a comment below. Other than that, if you like this video, hit the like button, and I'll see you guys in the next video.